Hello everyone, welcome to Digital Electronics and Computer Aggregation course. I am Sudhakar Ajmera, Assistant Professor, Department of BC, MLR Institute of Technology, Hyderabad. In previous sessions, we have discussed about various logic gates, and today we'll see about Boolean Algebra, theorems, properties and postulates. As a part of this Boolean Algebra, theorems, properties and postulates, we'll see the overview. Boolean algebra is a mathematical system for analyzing and simplifying logic circuits, and it's a branch of mathematics which is developed by George Boole in the year 1854 for minimizing the Boolean expressions. While designing any system, digital systems, we required minimized equations. To minimize these equations, a Boolean algebra was designed, and it is mostly used in digital logic design and switching circuits. So Boolean algebra, theorems and postulates will be used in minimizing the Boolean expressions. As a part of this, we will see few properties, postulates and theorems. First, we will see what are the important postulates here. So as a part of these postulates, here important is the set is closed under and or operation under closure postulates. And as per identity postulates, if we add 0 to some variable a, we will get a, and if we multiply any variable with 1, we will get same variable. So what I mean to say, if we add 0 to any variable, let us say here in this case we got a, and if we multiply 1 with any variable, we will get same variable a. Next one, we will see commutative postulates. As per this commutative postulates, left side if you observe, a plus b will become b plus a. So what do you mean by this? If we add a with b, and if we right side, if you see, variables was swapped. The same way, if you see this one, next expression, a cross b is equal to b cross a. So what we have done here is just swapped the variables of left and right side of equal. So as per distributive law, if we take a followed by b plus c, multiplication of a followed by b plus c term, as per this we will get a dot b plus a dot c. So here this dot operator will be distributed over this term b plus c. So here as per this, here first term only a, in second term b plus c. In between this first and second term, dot operator will be there, and this dot operator will be distributed over this term b plus c. So here a dot b plus a dot c will come. Now as for complement postulates, if we take true value a and its complement value a bar, its complement value a bar, and if we add together, we get 1. In another one, if we say variable a, true value a, and its complemented value a bar, and if we multiply these two, true and false value, a and a complement, the answer is 0 as per complement postulates. So these are what important postulates in Boolean algebra. Next, as per this Boolean algebra, we also have few important properties. That is, one is idempotent law. So as per this idempotent law, if we take any variable or expression a, and if we add same variable again a, not only a plus a, we can take any variable, another variable also. If we add same variable, we get only single variable. In the same way, if we multiply same variable, A cross A will get A. So as per null law, if we take A variable, for example A variable, and if we add 1, answer is 1. So what I mean to say, if we add 1 to any variable, A or B or C, whatever it is, we'll get 1 only. Not only variable, it is true for any expressions also. And if you multiply any variable A with 0, we'll get 0. Next one. So domination law. As per this domination law, if you add 0 with some variable A, we'll get A. And if you multiply 1 with variable A, we'll get A. Next one. As per double negations law, if you take A variable and its complement, again if you do complement, so what does it mean? We are doing double negation. We'll get true value A again. So this is about few important Boolean algebra theorems. Next, Boolean algebra properties. Next we'll see Boolean algebra theorems. So as per this Boolean algebra theorems, De Morgan theorem is very important. As per this De Morgan's theorem, it says that A cross B bar is equal to A bar plus B bar. In the expansion, what we got is, if we take A dot B whole bar is equal to, we need to interchange operator. So here dot operator is there. So here I'll take plus operator and complement each literal, A bar plus B bar. Or else, if I take A plus B whole bar, so what I'll do here in the expression, in the expansion, A dot B. So what has happened here? This plus become dot and complement each literal or variable. So De Morgan theorem says that in the expansion, OR operator can be replaced by AND operator, and AND operator will be replaced by OR operator, and vice versa, and complement each literal. So this is about De Morgan's theorem. As per involution theorem, same thing. We have seen this previously. So A complement of complement is become A. Next one, duality principle. As per this duality principle, AND operator will be replaced by OR operator, vice versa. And it is true for logic 0 will be replaced by logic 1 and vice versa. This is called as dual expression as per duality principle. If we see consensus theorem, if we see the consensus theorem, you take true value A and its complement value A bar. True value A, its complement value A bar, and if you multiply this true value with some variable B and false value with some variable C, and whatever values we have multiplied here, B and C, take its product, add together, will form AB plus A bar C. This is what consensus theorem. Next one, redundant literal law. So here variable will be in redundant form. So as per this, if you take redundant law, A plus AB is equal, we can take common of A and we can write 1 plus B, because in this term A was common and from first term we get 1 plus in next term we'll get B. So as per previous laws, A of B, because as per previous postulates and laws, anything, if we add any variable or any logics, if we add to 1, it will become 1 only. So as per that, A of 1 plus B is nothing but 1. So answer is A. So this is true for this expression. So as per redundant literal law, we will get A plus AB is equal to A. These are important theorems while minimizing. Let us see how to represent some logic gate. For example, I have taken AND logic gate. So NAND logic gate. So as per this, NAND logic gate expression is A plus B whole bar. How we can write A plus B whole bar is equal, as per previous theorem, De Morgan's theorem, you can observe A plus B whole bar, we can write A bar dot B bar. So here what operators I have used? Actual expression for NAND logic gate is A plus B whole bar. To implement this, we have used OR operator, NOT and AND. This is how we can represent NAND logic gate in terms of AND logic gate, OR logic gate and NOT logic gate. We can observe here, this is what AND term, this is what OR term, and this is what AND term, and these are what complement terms. So NAND gate equivalent is in terms of AND gate, OR gate and NOT gate. So using these properties, postulates and theorems, we can minimize the Boolean expressions. For example, I took first example, A plus A bar B, A plus A bar B. We can minimize this. So here, as per absorption law, how we can write this one? So A plus A bar dot A plus B. So here A plus A bar is 1, as we have seen in previous one, and A plus B. So now this term will become 1 and this is as it is. So 1 dot A plus B is nothing but A plus B. So here we have minimized this expression and we got A plus B finally. Let us see example 2. Let us see example 2. A plus B into A plus C. A plus B into A plus C. Let us multiply these two terms. A dot A plus A dot C plus B dot A plus B dot C. From this we can get it, A dot A is A only, AC plus AB plus BC. From these two terms, we will take A as a common. So 1 plus C will get plus AB plus BC. We can get it, right? So next one, A into 1 plus C is nothing but 1 only as per property. Next, AB plus BC. So what we got here, it is A plus AB plus BC. So from this I can take A again common. So what I can write? A of 1 plus B plus BC. So here A of 1 plus BC, because 1 plus B is nothing but 1 only. So here you can write, finally we'll get A plus BC, because A dot 1 is A only. So from this A plus B into A plus C, we got A plus BC minimize equation. So like that we can use these theorems, properties and postulates in the minimization of equations. Now coming to the applications where we can use this. So applications, we can use this Boolean algebra theorems, properties and postulates in designing the digital circuits. It is very important. To design digital circuits, definitely we need to use Boolean algebra theorems, properties and postulates to get minimized equations. And these Boolean algebra theorems, properties and postulates simplifies complex logic expressions. And wherever you want to reduce the hardware components, there also you can use this Boolean algebra theorems, properties and postulates. And it is essential in computer architecture and embedded system designing. Uses of minimization. Why one can use this minimization of Boolean expressions is it reduces circuit complexity and it saves cost and space. It increases speed of operation and it reduces power consumption. It improves reliability. It enhances performance in digital systems and it facilitates easier debugging and maintenance. That is why one can use minimization of Boolean expressions. As of now, we have discussed Boolean algebra theorems, properties and postulates. Finally, I want to summarize. So, Boolean algebra provides the foundation for digital logic, and theorems and laws simplify circuit designing used in CPUs, microcontrollers and digital systems. Example, embedded systems. So, today we have discussed Boolean algebra theorems, properties and postulates. In upcoming session, we will see K-maps representation. Thank you.